You're good, no worries. So, I believe where we ended was looking at the double arrow. Said the double arrow is kind of the new concept, our reaction arrow in between. So we covered real quickly the basics of what an acid was. What was the acid? Okay, that's useful. Yep. It is known as a proton donor. If we're going to use English, if we're just going to write out what it is, we're exchanging H+. So it's a loss of H+. So if we take a look at the acid to then the conjugate base, all that changed to that structure is it lost a hydrogen. If I go through and take a look at the H2O, it looks most like the other piece. All that changed was that it accepted H+. So we're recognizing acids and bases based off of that definition, right? Because that's the easy or the most usable definition. Right? If we go through and define the species on the right-hand side of the equation, we run into a bit of an issue. Because H3O plus, to come back to H2O, because they're conjugate partners of each other, H3O plus would have to act as an acid. It has to lose a proton. Right? So if I ask for the acid, it then becomes questionable. Am I referring to the acid on the left-hand side of the equation or the right-hand side? Right? Most chemists seem to refer to your acids and bases being specifically located on the left and the conjugate partners being on the right-hand side of the equation. This allows for a simple way to differentiate which one's which. Okay? I say most because the people that wrote the final don't agree with me. And we'll leave it at that. Okay? So the part that's tricky here is that double-headed arrow, or that double arrow, saying that the reaction can go both forwards in our standard format, left to right, and in our non-standard format, right to left. Right? This means both sides of the equation have reactants and both sides of the equations have products. And what's happening here is that when we think about chemical reactions, the way we've discussed them, they only go one direction. Okay? Like a car, it can only go forward. So if you buy a little power wheel for a little kid, they have a button, and they push the button and the car goes forward. I found out because my father-in-law bought my son a car. Okay? Push the button, it just goes forward. Okay? Super exciting for a little kid because they get on it and they just move forward. Okay? Why does it not have reverse?
You can't see them.
Okay? Little kid isn't going to be going forward and go, oh, actually, let me turn around here. Because the instant they do that, what happens? They fall off or they crash the bike. Okay? So we use training wheels effectively to only allow them to go forward for an instant. Okay? We don't allow them to see that you can go backwards at the same time, even though that all cars have that ability. Because we want people to get used to the forward direction first. Guess what happens in chemistry? We only look at the forward direction, or we look at the forward direction first until we get somewhat comfortable with reactions and dynamics and how things move around. Okay? Once we're used to that, then we pull the carpet out from underneath you and say, actually, reactions go both directions. So when I run a chemical reaction, it doesn't just go left to right. It also goes right to left. Some of those products will react with each other to make the reactants again. It changes our whole worldview on chemical reactions. But that is what happens in chemistry. Okay? All of our reactions are dynamic. This comes with the concept reversible reactions, which is equilibrium. Most of the chemical reactions that we tend to study in general chemistry are non-reversible. They only go one direction. Okay, why? It's easier. Okay? Why else might that be important? Okay? We could look at other things that we need to learn to process into that. Okay? If you want to build a building, do you want to build it in such a way that it starts to fall apart right away? No, we're trying to build something that stays permanent, right? As chemists, what are we trying to do? Build something that stays permanent. So if I'm going to try and build something that's permanent, the reactions I'm going to choose to evaluate and study are going to be the ones that don't reverse. Right? So I will select the equations and the reactions that are important to me, and those reactions will tend to be the ones that do not reverse, so that when I build something, it stays as a permanent structure. Right? That's why most chemists tend to study non-reversible reactions. Does that mean the reversible ones aren't important? No, the reversible ones are incredibly important as well. Biologists tend to study those a lot because that's what our body does. Our body reverses reactions all the time. We have to have that flexibility. Okay? So we need to be able to study it and come up with ways to quantify it. This is the concept of equilibrium. It is a complex enough subject that an entire chemistry course is devoted to equilibrium. That's Chem 152. Right? You spend pretty much the entire semester talking about equilibrium and, unfortunately, how to quantify it, which is even more phenomenally interesting and fascinating than my voice belies. Okay? The big deal about our equilibrium comes down to this famous guy, Le Chatelier. We have Le Chatelier's principle. Okay? All chemical reactions will achieve an equilibrium, given enough time. Okay? Once they are at equilibrium, they will do whatever it takes to stay at equilibrium. Okay? That means I'm happy, I'm settled, but now you're going to give me a test. No, I don't want to deal with the test. I'm going to get rid of it, not think about it. Okay? We're going to try and come up with ways to avoid looking at that system or change back to our happy state. Okay? Like maybe after the test, you change back to your happy state by going to Disneyland. Why not?
Playing with puppies.
Okay? Playing with puppies. Okay?
I was keeping my mouth.
I was trying to avoid that one. We've gone enough down that path, I think. Okay? So we're coming up with ways to reobtain our balance in life. Okay? Same thing is happening with chemistry. Our reactions will try and re-achieve that balance by changing the direction of the reaction. Okay? So what do we mean by that? So equilibrium and Le Chatelier. This, unfortunately, is becoming less and less common. Does everybody know what a seesaw is?
Yeah.
Okay, so let's work with the seesaw one, because I think the other one's a little bit, dangerous. That's exactly the word I was hoping to hear. Not really. Okay? So, seesaw, right? We've got a seesaw, we got a little thing in the middle, and we get a little happy kid on one end of it. That's my happy kid. See, he's smiling. I don't know why his head is floating. Okay?
Does he only have one eye?
And then we get another kid that's up here that's really smiling, because he's like, oh yeah, I'm going to jump. And he jumps on, and what happens?
The other kid
Launches the little kid. So yeah, probably not smiling anymore.
The other kid becomes a unit.
Okay? So what's happening, and that's why we got rid of seesaws. Okay? So what's happening is we have a balance between those two, right? So if those two kids, that's an eraser. That's just going to be my kid. I'm done with it. Okay? We're the same weight. They could kind of jump up and down and they get this kind of fun action. But what if one kid was a lot larger than the other one?
Would they laugh at him?
Is the seesaw quite as fun? No, because what happens?
The one end stays down.
The one end just stays down. The little kid is now up in the air and is stuck up there wondering, what the hell, how do I get down? Okay? So it's looking at physics and how those two sides can balance out. Okay? And balancing out is when they are of equal size. So let's go through and now look at chemistry. Except chemistry now, because I'm horrible at drawing little kids, is just going to look at a box. So there's a reactant and there's a product. Okay? And we'll have to kind of pretend that I'm drawing these roughly the same size. Man.
Not even close.
Come on, teach. That looks like a jello.
It's okay. The width makes up for that.
We get it.
No, it's too big.
Perfect.
That's actually not too bad. Okay, so now they're even size. Our reaction has achieved equilibrium. The board is now balanced. Okay? And one of the issues with this now looks very static, and that doesn't work for chemistry. Chemistry isn't static, it's constantly moving, and that's where the other example comes in. Right? But this is where Le Chatelier comes in and says, okay, well, it's now achieved equilibrium. The reaction is happy where it is. Right? And as soon as somebody gets happy, what has to happen?
Has to change.
The world comes along and says, I won't swear, but sure. Right? I'm going to mess with you a little bit.
Please say that.
So I'm going to mess with you a little bit, and I'm going to put some more stuff over here. What now happens to the seesaw?
The seesaw goes down on the left side.
Goes down on the left side, it comes out of whack. It's no longer in equilibrium. Okay? Well, chemistry goes through and says, well, I want to be at equilibrium. I'm going to do whatever I have to be equilibrium.
So it has one to its own.
So what does it do?
Yeah. Fights the other parts until the other parts.
Okay? So one option, right, is we add more to the other side. Right? But Paul should complain on this one. What's the issue with just adding more to the other side?
Where are you getting it from?
Where the hell did it come from? Exactly right. We can't do that. We can't create matter. So that doesn't happen. Right? So how can I make sure it achieves balance?
Get rid of that matter.
I can't destroy matter.
You share the matter between the two.
I don't share it. I
Destroy it.
convert it
Ooh.
through a chemical reaction. I take my reactants and I convert those into products. So I will take a little bit of my reactants and add those now over to the product side. Let's just say that's close enough. I don't know why I took out a weird shape, but I did.
Looks like an apple.
Now we've achieved a balance again. Okay? That's Le Chatelier's principle. Once we are even, the reaction will do whatever it has to achieve that balance again. Okay? One option was that we get rid of or we add a whole bunch more reactants. Well, that's going to force more products to form because it wants to get back at that equilibrium spot. What else could we possibly do to this to mess with it?
Move your fulcrum or your triangle.
Yes, too hard. But yes, we'll come back to that. What else could we do to mess with this?
Move the products that you have.
Right? How about, now that it's happy and balanced at equilibrium, I go through and remove a bunch of products. Heck, let's just remove them all. Now what happens?
And now it is. One second.
Now it's imbalanced again. What does the reaction do to re-achieve that balance?
It shares it.
It converts it.
It converts some of the matter that's in the reactant side and it makes that a product.
It shares its toys.
Doesn't that have to happen in certain quantities though? In
No.
ratios?
Now, what dictates how much product is made, right, and the relative amounts back to reactants and products? That comes out of the chemical equation, right, for the amounts of each of those, and it's also going to be determined by the fulcrum, which we'll come back to in a second. At this point, we just tried to pick the easiest fulcrum first. Okay? What else could we do? So we've added reactants, we've removed products.
Take what we have and split it between the two.
Well, if the more can we apply force to one side?
So that's getting too into the physical of this. This is literally just trying to look at the balance of those the chemicals within a test tube. How about I add products?
You have products.
Right?
Can you heat it up?
We'll deal with heating it up later too. If I add products, now what happens?
It's unbalanced again.
It's imbalanced again. So what does the reaction do?
Balance it.
It's going to convert those products back to reactants. There's the double arrow.
Dun, 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 dun. Is it really how you spell Seesaw?
I don't know.
Yes.
Is it really?
Okay, see, I'm not horrible.
That's serious.
That horrible.
No, I was just
And we now have equilibrium, and that's the balance between it. Okay? What this assumes is the amounts, relative amounts of our reactants and products are constant, are equal. Okay? All things considered, that's a crap reaction to run. Why is that not a good reaction?
because we want more product in the reactor.
Right? If I'm going to run a reaction, do I want products or do I want reactants?
Products.
I want products. Right here, yes, I'm producing products, but I'm not getting a lot converted across. I have a lot of reactants left over. Okay? So what would I change about this to make me get as much products as possible?
Move the fulcrum
I could move that fulcrum. Where would I move it?
closer to the product side?
Close to the reactants.
Okay.
I think. I don't know physics very well.
Okay.
I'm trying this. So.
To the left. Sorry. Bad. Let's move it to the left. What happens now?
Product
You
side
need-
goes down.
Do you need less
The product
reaction?
side is going to be leveled out or flattened. How do I get the product side up?
Make it
Put in more
lighter?
reactants on.
I need less weight on the product side, right?
So it does need to be towards the product side.
And what ends up happening? I would need less weight over here and more weight over here to account for that imbalance,
So it was right. It needs to be closer to the product side.
right? And that then takes us to this situation where I have a lot of reactants and very little products. Is that going to be a useful chemical reaction for us?
No, not at all.
No, that's a horrible chemical reaction for us because we put in a ton of reactants and we get nothing out of it.
Oh,
That's not a good choice. So if we were given the option, we wouldn't want to use this chemical reaction. We would prefer the chemical reaction where that fulcrum is located way over to the right. And what does that then mean?
You need a lot on the
A little
product
bit
side.
of
Very
reactant,
little
there's a
reaction.
whole lot of product.
A very small amount of reactant gives us a very, what did I
think
say?
we could have more products.
Very small amount of reactant gives us a large amount of product. Right? This is the concept of equilibrium. And we quantify this by comparing the amounts of product to reactant. Right? So we're saying once we are at equilibrium, so now that I'm here, I want to quantify this so I can then relate this for everyday systems or for my equilibrium. Okay? Why did we pick K to describe equilibrium? Because everything else was taken. I don't know. That's what we got.
But that's potassium.
Okay? Yes, it could be confused with potassium. It is not potassium. K is our equilibrium constant. Okay? If I want to quantify it, it does kind of look like a seesaw. I want to now look at the relationship between the amount of products to the amount of reactants, which gets me two ratios. I could have products over reactants, or I could have reactants over products. Everybody see that? Which one do we choose?
Products over reactants.
Products over reactants.
Because that should be part of the whole, right? So you can't have more product than your reactant.
We'll address that different. We aren't creating matter, that's true. So the total number of particles within our system are constant. It's just a question of where those particles are located, okay, be they products or reactants. So now I can go through, since I've got this expression now, and I can look at K values to understand something about that chemical reaction. Okay, the K value is telling me where that fulcrum is located. Okay, in this case, I want the fulcrum located as far to the right as possible so that I get a large amount of products, right, and tiny amount of reactants. What would my K value be expected to be? I would expect a very large K value. So reactions that have large K values are good. Okay? Those are ones that we tend to favor. Those are the ones that you tend to see in general chemistry. Every chemical reaction we've looked at this semester has a massive K value because it almost exclusively produces products. Okay? What would be a bad K value?
Because if it was extremely low or negative, can it even be negative?
Could it be negative?
No,
Why not?
because you can't have nothing of something, you can't have less than nothing.
I can't have less than nothing of something. Okay? I can't have a negative value of reactants. My reactants can change, but I can't have a negative value for them. Okay? So that means what I'd be looking at is a K value that is very, very small, but very, very small in comparison to 1. Okay? This would be a bad value. What's that?
All real numbers greater than 0, less than 1.
All real numbers greater than 0, less than 1 would be a bad value. Anything that's really, really big, officially bigger than 1, is a good chemical reaction for us to run. Okay? Does that mean we ignore the ones that are bad? No, we will still have to evaluate those at some point depending on what systems we're looking at. And those can be used to control reactions to allow us to do different things. Right? So those aren't inherently bad, they just don't produce a lot of product. Right? Our good ones, as our quote-unquote, produce a lot of products. So when we're looking at our chemical reactions, we can quantify these based off of this K value, which is just looking at the ratio of products to reactants. Okay? What units? Don't worry about it unless you take 152. Okay? You guys had some questions?
I was just wondering about that. It looks like you have a double inequality or double equality sign.
That's not a double inequality, that's saying really, really small.
Okay.
Or really, really smaller than 1. Really, really bigger than big. Yeah. Okay. So this was a very static example with the seesaw. So let's attempt to quickly look at one that's a little bit less static. Okay, because this is a little bit more like what's actually happening in a chemical reaction. I have two divided chambers with a reactant and a product. Okay. When I start a chemical reaction, typically how much product do I have? None. Okay, so let's go ahead and put a barrier at the bottom of our chemical reaction. Okay, and what we're looking at is passing through that to form those products. And I'm going to fill up the reactant side. And now I say, reaction, do your stuff. Okay. Magic ensues, and what happens? The barrier at the bottom is removed. What happens to the liquid in the reactant chamber?
It goes down and products go up.
It drops. What happens in the product chamber?
It goes up.
It goes up. Until eventually what happens? They're even across them. We've reached an equilibrium. Okay, and this is a better example of our equilibrium. Is the liquid on the reactant side now no longer moving to the product side?
No, it's shared.
It is moving over to the product side. It's not all of a sudden there's now a barrier. There's no barrier there. It's constantly moving across to the product side.
And the product side is constant, correct?
But if it was constantly moving over to the product side, wouldn't the reactant side drop?
No,
Why does it not drop?
they're sharing.
Because the product side is constantly moving back to the reactant. This is where equilibrium really shows its truth for chemical reactions. We're not talking about achieving an equilibrium and now everything's done. It is constantly oscillating back and forth. What we're saying is the rate of the conversion from reactants to products is the same as the rate of conversion from products to reactants. They are constantly moving back and forth. Constantly moving back and forth. You mean kind of like
Seesaw.
our double-headed arrows? Yes, that's exactly what's happening here. We can still apply Le Chatelier's system to it. Let's pause the reaction. Now I want to put in some more reactants. I wave my magic wand and I say, reaction, be free. Now what happens?
They even out again.
The reactant level will drop and the product level will increase until we achieve
Equilibrium.
a new equilibrium. The value for K will be constant. Right? The amounts of those will stay the same. We're still constantly moving back and forth between those. The problem with this example is this is a lot more difficult to deal with when we consider our actual chemical reactions. Because this says the amount of reactants is always equal to the amount of products, right? Everybody see that? Okay. But that's not always true. How could I change the fulcrum? Well, there's no fulcrum to change this. Right? Let's say I take some product out. So I paused the reaction. I remove some of that product. It's now down here. I now start the reaction. What happens? It equalizes again.
Just lower.
It's all going to deal with that center bar. Okay? Where that center bar is located is what's going to allow us to kind of differentiate amounts on these. If I slide that center bar extremely far to the left, now what happens? Okay, I'll have a lot of products and very little reactants. If I slide that center bar further to the right, a lot of reactants and not very many products. Okay? So it's all now a question of where that center bar is located. That center bar is our equilibrium constant. That is the value for that individual chemical reaction. Okay? For those of you being like, wow, this is kind of a hard concept, it is an exceptionally difficult concept. Hence why there's an entire class that talks about it. Okay? And usually goes through and quantifies the crap out of it. Okay? Anybody in any kind of engineering field will probably have to do this.
Yeah. Is there a way to see that reaction? Like color change and heat?
So there are ways that we can visualize equilibrium. There's something known as the clock reaction. So if you want to take a look, YouTube that. If I had been paying attention, I probably should have pulled up a video for that, or even the demonstration. There's something known as the clock reaction that will cycle back and forth between reactants and products. Okay? As it does so, it changes color. Okay?
So it's like constantly changing color.
But at very specific times. Yeah, that's why it's called the clock reaction. Yeah. Okay? So what things now affect this? So remember, what we talked about here is that we're concerned about the reactants forming products and the products forming reactants, that it's the rate of those reactions going back and forth. Right? So what things might affect that rate? Okay. Heat, temperature, pressure. Pressure is going to affect a liquid reaction. To dissolve a solid in liquid, what do you do to the temperature? You increase it, because you're trying to take the solid and break the intermolecular forces to turn it into a liquid. What do you do to the pressure?
Nothing.
Nothing. Does the pressure affect our liquid reactions? No. Okay. It can affect gas reactions. So we have to be careful when we're thinking about things that affect the rate and what we're actually quantifying within those systems. Okay, so concentration. The amount of things present can affect the rate of the reaction. Okay, we could scale this much higher and we could look at you finding a significant other in this world. If you are the only person in the world, how likely are you to find a significant other?
Not at all.
Not very likely. Okay? Because you are by yourself. The concentration is effectively zero. You're not going to have a reaction. If there's one other person in the world,
Even less.
Still low.
still really low, because the concentration isn't high enough. Okay? If we move up to 3 billion people, what are the odds of finding a significant other now?
In the negatives, just a little bit.
A little bit better, because our concentration has gone up significantly. You've increased the amount of interactions between those individual particles. You're increasing the chance for the correct connection to be found. Okay? Does that mean the connection is going to be significant enough to create that connection? No. Okay? You could be wandering through the world and back into your significant other, never see them. Does that mean you're going to now become significant partners, for lack of a better description? No. So is there something else that affects it? Perhaps the orientation of those particles. Right? Maybe the energy. You're in the proper orientation, you can make eye contact with that future significant other, but you are so beat tired from the chemistry test you had that morning that you can't even speak. You got drool coming out of your mouth and you're just staring there. They're probably like, nope, thank you, I'm going to move on. Right? So there's an energy associated with it. We've got a variety of things that kind of contribute. The nature of the reactant. Right? Liquid particles or solid particles have less movement. The less likely they move, if you stay stuck in this room, what are the odds you're going to find your significant other? Pretty low, because you're now requiring that your significant other comes into this room to interact with you. Right? So we want to increase Motion of the particle. So what phase are we looking at? Surface area. How does the reaction proceed? Perhaps the only way you can interact with your significant other is if you're both doing handstands. I don't know. Why not?
Well,
Right? If you're both doing handstands, then now you can be partners. So how does that reaction proceed? What things have to happen to allow that reaction to occur? Okay? Temperature. There has to be enough energy associated with it. Okay? Catalyst. Maybe you have a best friend that then introduces you. Okay? That's a catalyst. All of those things contribute to chemical reactions in some form or another. It's just a question of how we quantify those.
Blindly tap your pen.
When we think about our interactions with significant others, do you just walk around and be like, bump, hey, do you want to mate? That does not work very well, right? Okay? What are atoms and molecules doing? Bump around, hi, pleasure to meet you. I'm so-and-so. I've got this many degrees. You should date me.
I prefer not.
No, they probably just bump. No, that didn't work. No, that didn't work. No, that didn't work.
I want to see
Okay.
you in it.
There's complete blind, zero communication that's happening. When we're looking at our interactions with the real world, we're trying to think about those relationships. We're trying to add or personify those. Chemicals can't do that. Okay? This is literally them just bumping into each other and saying, was that the perfect orientation? Nope, let's try again. Okay? I'm just going to spin around freely until something happens. This is where blindly capping your pen comes into play. Okay? If you uncapped a pen, okay, put it down on the table and then just try to randomly cap those things with no other information, it's going to be harder for you to do than you think. Okay? What things could happen that would allow you to better or more likely cap that pen?
You have amazing hand-eye coordination that you can measure.
Sight. You mean there's another piece that's somehow allowing you to catalyze putting those two pieces together? Yeah. Okay. Or maybe feeling that one end has ink on it, because, I don't know. Yeah, I don't know. You feel it and it's pointier than the other. So you know that's the one that you got to cap. Okay. You're adding some other kind of catalyst or thought behind it that chemistry can't do. Okay. That's what's happening with that example. So when we're looking at our chemical reactions, we have to understand something about rates and equilibrium. Both of these topics show up in second semester general chemistry, and they're both incredibly complicated, but they're also pretty fascinating, the things that can come out of them. Okay. How does this interplay with our acids? Okay. So H2O. H2O's equilibrium is described right there above it. We've got its fulcrum. How do we know that to be H2O? And even that's not quite true. Water is nice and evenly balanced. It's a neutral system, right? What about HCl? What do you know about HCl?
It's an acid.
It's an acid. Why is it an acid? What did it do to act as an acid?
Has the hydrogen.
So did water.
It's got the one hydrogen.
Okay, it has one hydrogen. Water has two hydrogens. Why isn't water a stronger acid than HCl?
Because that's not how chemistry. The charge is balanced.
Because of what it's bonded to.
Okay, so we can look at something about what it's bonded to. Okay? What makes it act as an acid is that it gave up that hydrogen. That it formed H+. That H+ now wandered off. That I don't have HCl anymore. I have H+ and I have Cl-. Why is HCl a strong acid? It produces a lot of H+. Very little of that compound stays HCl. What does that mean about my equilibrium?
Very skewed.
It's very skewed. What does that mean?
It's more towards the
One's
reactant
one
side.
side stronger than the other.
A little bit of HCl mixed up with also T on the website.
So we're saying we have a lot of HCl and a little bit of H+ and Cl-, right? Because that's what that one means, right? We have to have the big one to counteract that small weight because the lever arm. Oh, that's right. Doesn't line over there. What we're saying is we have a little bit of HCl and we have a lot of H plus and Cl minus. So I can look at HCl, and by addressing that I know it to be a strong acid, that its K value is really, really big. The one underneath is known as close to acetate, but it has the hydrogen in front, so we should be calling it acetic acid. Acetic acid, is that a strong acid? No, I don't know. Fair answer at this stage. No, it's not. What does that mean about its equilibrium?
It's not giving up a whole bunch of.
It's not giving up a whole bunch of H+. In fact, it's giving out a very small amount. We would have an equilibrium that's more along these lines. So if I use equilibrium, I can explain something about the strength of my acids or my bases. Okay? That's kind of the point of equilibrium. It can help us quantify those relationships a little bit. Okay? So there's our products over our reactants. Back to this strong versus weak. I'd have to go through and quantify. That's not particularly fun. Okay? Strong acids completely ionize when they hit water. Okay? This means they're strong electrolytes. They produce only the ions. They don't have the molecule anymore. That's HCl. Okay? If we have tons of ions, that makes them electrolytes based off of the lab you did last week. Because if I stick electricity attached to a light, what happens to the light when I stick it in a strong electrolyte? It comes on. Electric light. There it is. Okay? Weak acids and bases vary their ionization depending on their different systems, depending on the chemical bond nature found within them. That's largely discussed in second semester 152. So how can you look at a formula like HCl and be like, that's a strong acid, or look at HC2H3O2 and know that that's a weak? We can come up with rules if we were in organic chemistry to explain the relative strength and weakness of those, but it wouldn't establish which one was strong or weak. It would just say one is stronger than the other. We're not in OChem, so we don't do that. So how do we figure it out? And what I tell you is that your strong acids are perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. Your strong bases, like lithium hydroxide, calcium hydroxide, group 1 and 2A cations bound to hydroxide. Those are defined to be your strong acids and bases. Okay? So what this ultimately means is you would have to have these memorized. Do you need it for this final? Don't worry about it. Okay? But that's why you know hydrochloric acid is dangerous, because you were already instinctively told to have that content memorized. Okay? Where's HC2H3O2, or acetic acid?
No.
Not on that list. What does that mean?
It's weak.
It's weak. That's it. That's how you decide between strong and weak. You know the strong, everything else that's not strong is weak. Just like polar covalent. How do you know you have a polar covalent bond?
It's everything else.
Metals and non-metals.
Metals and nonmetals would be an ionic bond. I asked for polar covalent.
It's everything that is not ionic or...
It's everything that is not ionic or non-polar covalent. Okay? Same thing is happening here with our weak acids and bases. Okay? If we go through and think about safety, okay, if we were going to go through and try and describe to little Timmy, hey, watch out for that solution because it has a high concentration of hydrogen ions in it, it'll burn you. Right? That's a lot of information, particularly because we used hydrogen ion, H+. Okay? Little Timmy can probably barely speak, and we're trying to use chemistry terms. We then throw in the unit of molarity. How many of you had heard of molarity before this class? Ouch. Right? So that's not going to help us out either. Okay? Then we also have a decimal. Okay? Little Timmy barely speak, can probably not deal with numbers very well, and we're throwing in a fraction at them. Probably not going to figure this out. So what do we develop as scientists to say, hey, watch out for that solution?
Strong acid, don't
We could say it's a strong acid. Watch out for that.
Some brightly colored sticker.
We could use a brightly colored sticker. Right? We could go through and determine a pH. Right? The pH system is a beautiful system because we have ways to identify different concentrations of hydrogen ions based off of color. So the pH of the solution is merely a way to monitor the amount of hydrogen ion in an individual solution. Right? If there's a lot of hydrogen ion in that solution, it becomes acidic, okay, and it would be a red solution. If there was a lot of hydroxide in that solution, it's now basic, and it would be a blue solution. So we can use kind of a color spectrum between red and blue and how our indicators change to represent that. We would also want to be able to quantify this with numbers. Okay, remember that farmer that I made fun of, and I'm a horrible person for doing it, that couldn't count higher than 20? Or 12? Doesn't matter. Okay.
10.
No, it does matter. We can't count higher than 20. Okay? We want a numerical system that we can achieve relatively easily with our fingers and toes. So I don't want to go beyond 20, and I don't want to go less than 1. Because I can't go through and say, well, it's 1 knuckle worth of reactivity. That's a bad analogy. Okay? I don't want to use fractional systems. Okay? So that's where pH also comes in handy. pH will allow us to monitor the concentration of hydrogen ions and hydroxide all at the same time, and now use a system to convert those numbers between 0 and 14. Right? And if I have a solution that is at a 0 pH, I now know that that solution is super acidic. And a solution that is at 14 pH is basic. Okay? Both of those solutions, seeing either the pH number or the color associated with them, would make me say, I don't want to stick my hand in that.
How come bases are higher numbers than?
The reasoning behind the numerical system comes from how it's monitored, which comes to what pH is. pH is the negative log of the hydrogen ion concentration. Right? How many of you are like, concentrations, I got it, I'm awesome, I know everything there is about concentration? Okay, so there's a problem. Negatives. How many of you are like, every time I see a negative, I use it completely and perfectly correct? Problem number 2. Log. Does anybody know anything about logs?
I know how to spell.
Please talk to me after class, because I have no clue about logs. I really don't understand them.
It's calculus.
That doesn't help me. Right? So we have 3 systems involved in that calculation that we all have problems with. If you want to quantify and look at where those numbers are coming from, by all means, we can go through and do that, and I can discuss that information, but after class. What I want you guys to get out of this is that pH is, by definition, the negative log of the hydrogen ion concentration, which is officially related to hydroxide through water, blah, 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 as I think was appropriately said back there. Last part, which you guys should already be rock stars at because of the lab, electrolytes. Okay? Electrolytes are anything that, when added to water, completely ionize. So a strong acid would be a strong electrolyte, because our strong acids completely ionize when they hit water. That's what they are by definition. A weak acid would be a weak electrolyte, because weak acids don't ionize as much. And we'd have to go through and quantify that. Okay? For the sake of my sanity and perhaps yours, I won't go through and label these according to strong or weak electrolytes. If you're concerned about it, please talk to me after class and we'll go through and do that. Okay? So we can label those. The practice that you had in lab was more than what you needed for understanding electrolytes. Okay, believe it or not. Questions? Right, so where that leaves us is to review. So, does anybody, having gone through and done the final, because I saw 48 emails from everybody this weekend over what questions they knew they absolutely had right on the practice final, right? Because I got those emails and I responded to every single one of you that sent those emails saying, this is what those answers were. Some of you are like, really? I didn't do that, did I? No, you didn't do that. One person did that. Okay? The rest of you are behind. Okay? So, what questions do you have? We can go through it straight in order, but again, I don't think that's as helpful as if you know where you have questions. Okay, actually, we may kind of dodge back and forth here. So, for 21, what is the maximum number of electrons that occupy the P energy level? Okay, so the reason I'm sitting down is what we really need to be able to see is a periodic table, which if I do this right, worked. Cool. So there's a periodic table. I know there's bright colors and it makes it confusing, but let's just deal with it. You should mark some stuff on your periodic table when you get your exam. One of the things you should mark would be relevant for this particular question. This is not relevant for this particular question, but charges are important. I don't want to worry about those right now. The blocks.
What number is this? Sorry.
This is 21. So those first two columns are known as the
S1.
S block.
S, yes.
Right? That means anything in the S block. Let's make it a little bit more obvious. So there we go. Our first two columns are S block. Okay. How about scandium to zinc?
P.
P.
D as a delta.
It's known as the D block. The next block,
The S block. P block.
the P block. And then the last block that we won't worry about at the very, very, very bottom, that's our F block. We probably won't ever have to worry about that unless you have somebody that wants to really push you in 151. Okay. Why is this going to be particularly helpful for answering the question? Because the question asked how many electrons are found in the P block. Okay. What does each column represent?
Levels.
Okay. So our columns, see if I can switch up. Each of these columns represent what? Adding one electron. So one electron, one electron, one electron. So every time I go through, moving from column to column to column, across a row, I'm adding a single electron. How many electrons could I add and still stay in the P block?
6.
6, because there are
6.
6 columns in the P block. How many electrons could I add to the D block? 10. S block. 2. F block. 14. You just count the columns. Okay? The periodic table has that information embedded in it. Okay? You have to remember the content that those blocks have some meaning associated with them. Okay? This goes back to, and I kind of hate preaching about it. The last exam, remember I said this information that you should write down on your periodic table? I think I saw one person write information down on the periodic table. Okay? Okay, maybe 2. Okay? Nobody else did. And then you're like, well, I don't know how to find conversion factors because you didn't write it down on the periodic table. That was the whole point of me spending 30 minutes in class telling you, write this information down so that you know where to find it. That's why I'm telling you. Okay? If you don't want to listen to me, that's okay. Just don't show up to class. Okay? Ideally, don't even take the test because you really don't care to listen to me. It's not going to help on the test. Okay? Which I find incredibly depressing, by the way. Okay, so if we go back to our question, because I can be optimistic, right? You're like, yeah, I don't believe you, Mike. You're lying. Okay. Maximum number of electrons that can occupy the p energy sublevel, well, it's just the number of columns. So it's 6 electrons, and our answer becomes B. Change the question.
Occupy the D.
Okay. So one option is instead of it being P, we make it the D energy sublevel, in which case it becomes 10, or our answer becomes D. Okay. For those of you saying, really, do I have to change each question? Yeah. Yeah, you should. Every question you go through and do in here, you should be able to change it at least 4 or 5 ways, because if you do that, you've then answered every question on the final. If you don't do that, then you're hoping that it just comes out and you get the exact same question. It's a false hope. Don't do that. Okay. How else could I change the question? Because I heard another option. How many in a p orbital? How many electrons fit in a p orbital?
6. 2.
2.
2 in each orbital.
There's only 2 electrons in any given orbital, period. Okay. Why can there be 6 in the p orbitals? There's 3 orientations. Okay. So you have to go back and review those terms and realize what those things mean. Yes, it's old content. You're responsible for it. Does that answer the question for 21? Okay. So 22. Which electron sublevel immediately follows the 3D sublevel according to increasing, it says, energy? Sorry, give me a sec. I need to move some stuff. So we go back to our periodic table, because this is where our periodic table comes in handy. Let's see if this works. Well, that was pretty ugly. Let's try that again. Yeah, that doesn't look very much better, does it? Let's try this. We're in the first row, right?
Yeah.
First row, first column. 1, 1. What does that mean? S block. First row,
1s1.
first energy level. Okay, so it's 1s, first column, 1s1. Okay, we would then move through. Helium is in the first row, second column. So 1s2. Lithium, second row, first column, 2s1. 2s2. This one gets a little bit weird.
Wouldn't that be the P block?
So depending on how you want to change your notation here, you could just go through and say 3, but we're now the first column within the P block. Arguably you could call this 1 P or P1. I think it makes a little more sense. Why would we keep the 2? It's in the second row. Okay. The periodic table fills. So, oh shoot, what was the question? After 3D? Okay. So we move down to where the d orbitals show up. Our d orbitals were that first block. The first row in the d orbitals becomes tricky because the first row is called the 3D. Why is that 3 weird? It's in the 4th row. So you have to remember that your transition elements are offset by 1. Okay? As we fill through 3D, 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 we would then move for our gallium. Which row are we in? We're in the P block. We're in the 4th row. So our answer, wherever that is,
Mary, was your email, yeah, you said differently, Mr. Nicola.
I'd have to go back and look at it.
I could show you.
Ah, where's my mouse? Go away. No, don't do that. Where's my mouse?
It's right there.
Oh, it just doesn't show up on my screen. Okay. What immediately follows our 3D? Yeah, it's our 4P. Yeah, I'd have to go back and check. Here, we can do this. Reconnect. Okay, do we want to do 23? Should be 4P, right? Because that is, unless I'm looking at the periodic table wrong.
Yeah, it's gonna be. Nickel, it's gonna be 3D, 8, yeah. Because that one's just 2, right?
I don't know what to tell you. 22 says A.
I'm referring to the email that you sent.
Oh, I don't know what to tell you. 22 says A.
You can talk to me after class.
Drunk answers.
I love you.
Paul. 23. Which of the following electron configurations for an atom of nickel? We'd have to go back, find nickel. Where's nickel?
It's in 3, it's in D.
3D block. It's 1, 2, 3, 4, 5, 6, 7, 8 columns over, which would mean 3D8. We can go through and take a look. We've got a 3D8 here. Oh, look at that.
So when it comes to questions like this, we only really need to look at the last.
Yeah, borderline. Okay, that's where you should start, is to look at that last section first, because that's the easiest check. After that, you should be backtracking through.
To make sure.
Okay, yeah, to make sure. Okay, I think I heard a 20. Did I hear a 20?
Sure. Right, 9.
20. Okay, so here's the demonstration for in class. My fist is now the nucleus. Where's the first energy level?
1s.
Where's the second energy level?
After that. Above it.
Where's the third?
After that.
Where's the fourth?
Above the third.
There's my chin, right? Okay. Which is higher in energy? Jumping from my chin to my right hand or from the third to my right hand? Why?
Because it's
Further away.
It's further away. So if we remember what that was 3 to 2 and my chin was 4 to 2. So 4 to 2 is more than 3 to 2. Yeah? So the answer would be E, 6 to 2, because that's the biggest jump. This is why we drew all those lines, to show those steps in energy. Sure. Next. Because we're actually starting to get a roll on 29. Maybe I should announce before I start scrolling, if people watch this at home so they don't get sick. Given the chemical formula sodium chloride, magnesium chloride, aluminum chloride, predict the formula for gallium chloride. So GaXCly.
They should have just.
Okay.
Has 1
So
CL.
let's use the information given to us. We have sodium, chlorine, magnesium, chlorine, aluminum, chlorine, gallium, chlorine. What should I not look at?
The other, those ones that are given.
How about chlorine? Why ignore the chlorine? It stayed constant through all of these. So really what I'm concerned about is, what does gallium, sodium, magnesium, and aluminum have in common?
They're all in the same row.
Oh, geez, calm down. Let me get a periodic table up. So let's go through and mark these.
11, 12, 13.
Sodium,
14.
aluminum, gallium, magnesium.
12. There you go.
Was that it?
Yep.
Okay. So sodium and magnesium are in the same row as aluminum. Gallium is in the same column as aluminum.
So they're all with.
So is there something in the periodic table as far as an organization that would allow us to say where we have trends? Yeah. rows are known as periods, columns are known as families. Do you look more like your parents or like me?
Parents,
Parents. Why?
because they're the same family.
They're the same family.
Well,
The name helps you out. Gallium will look most like aluminum.
So it's
It is E.
Shh.
Strike two, Michael.
Where did it go?
wait, what? What?
His email was like, gave us some answers that are.
Where'd it go?
I want this email.
Yeah, so, and you should have done your work and sent it to him, sunshine.
Whatever.
What is going on?
So excited.
There it is. Oh, come on. What is going
Mary,
on?
if the first answer was I drink a gallon of Japanese whiskey.
So, if we go through and take a look, what did we say? Gallium looks like
aluminum.
aluminum.
So the
So we're looking at GaCl3. We should have to take a look at it because you're numbering. It may, No, I'm not blaming it on you. I'm blaming it on a copy paste out of the email in. It may have auto numbered. It's done it to me a couple times and it's not been happy. Okay, that's fine. So our answer becomes gallium chloride because it matches the formula. We good?
yeah.
Was
Okay.
it the whiskey or the beer?
I spent the weekend sick, so
Not helping your case.
That's eggnog.
where's the mouse? Stop it, mouse.
Can't you just use like the down?
What was the joke?
It's too many different pieces of technology that are shuffling. Next. What's that? 19, and then I think I heard a 28.
42.
Blue, what are you?
19, oh, really? Do I gotta do 19?
Yes.
No. No, I think you're fine.
If we have to do it, you have to do it.
That was easy.
Yeah. It's just math.
Well, here's the thing, he's already done.
And we need.
So let's take a look at 19. What's happening here? Element Z has two natural isotopes, Z79, 78.918 AMUs, and Z81, 80.916 AMUs. Calculate the atomic mass of element Z given the abundance of Z79 is 50.69. Atomic mass is the average mass.
So you've only got 2.
Okay.
So you add
If you only have 2, we could add both of them together and divide by 2. Unfortunately, that will be wrong. It'll be close, but it's wrong. Why is that wrong?
Abundance.
If we just divide by 2, we are assuming they both make up 50%.
But
close.
he's 70.
It's
And then
close.
probably does, but it could not be.
But if we go through and look at our answer, there's 2 of them that come out darn close, 79.90 and 79.93. I'm going to bet one of those is the flat average and the other one is the weighted average. I'm not positive, but that's what I'm going
I
to
know
guess.
is the flat average, 93 is the weighted average.
So when we go through to do these, we have to consider the weighted average. That's the point of the percents. So it's the mass, sorry,
That's a lot of math.
let's try that again. The mass of one isotope times the percent of that isotope plus the mass of the second isotope times the percent of that second isotope. This then equals your atomic mass. Okay? So let's go through and make some simplifications here. I would argue Z79, for whatever reason, is just going to become A. So that means I know the mass of A is 78.918, the percent. This is where we got to be a little bit careful. When we put it into this formula, we need to be using decimals or the fraction.
0.569.
So up to you how you want to do it. I'll show you a couple ways. So there's the first one. We can put it in, it's just the decimal. You did the math in your head. I don't recommend that, but that's okay. The mass of B, well, the other isotope will be B. Its mass was 80.916 times the percent of B. Well, that's easy because it's right. Crap, not given an
Well,
equation.
you minus 50.699.
Because I know there's two isotopes, if I take the percent of A plus the percent of B, that had better equal 100%.
So it should be 49.
So I can find the percent of B, I'm hearing 49.31%.
31.
What does percent mean?
Out of 100.
Out of 100, so I can say 49.31 divided by 100.
That's literally.
Okay, which is 0.4931. Okay, well, you're saying, well, there's no difference there. Yeah, there is a difference. One, the difference, you showed the work. The other one, you did it in your head. That's it. If you do it in your head right, then there is no difference. If you do it in your head wrong, there absolutely is a difference.
You've got 75 seconds to do this problem, so.
True. You now have it. You can enter it in, and you're done. Okay.
If you divide
Can someone punch
I
that
already
in?
done it.
What'd you get for a number?
For your bottom one, it is 79.90. If you just add them together, it becomes 79.91.
And because I've got it, let's go ahead and just verify. Yeah, 19 is B. Comes out as 79.90 AMUs. Does that work? So unfortunately with that one, you have to remember the weighted percentage formula. Okay. How many times did that question show up in the exam?
Once or twice.
I think it only showed up once. You don't want to remember it? Don't. Accept that as a lost point. Okay? And for those of you saying, I need as many points as possible, you need as many correct points as possible. Your brain can only hold so much content. Decide what it can hold, pin everything you can on those. Otherwise, you're going to end up dumping too much time into questions that you're not going to get right from the beginning. It is okay to do that. Accept losses. I heard 29, I believe, first.
No. I think this is the other one.
We already did.
What was through?
Oh, we did, we lied, we did, sorry.
I think it was you. Oh, it was you? Okay. 28. Which of the following is a general trend from left to right on the periodic table of elements? This is another one from exam 1 where you just draw the arrows on the periodic table and you're done. Admittedly, I would probably have skipped this question. Yeah, you're like, but it's easy. Yeah, but there's so many words. It would just confuse me. Okay. So atomic radius increases, metallic character increases. So we're looking at atomic radius and metallic character. So let's pull up our periodic table.
Can we do all of the trends? Go to
It might just be easiest to pull them out in the textbook. Or actually pull them off the slides from Unit 1. That's going to be the best bet.
There it is.
Which elements are metals?
The first.
Left or right? Left. Okay. Which elements are nonmetals? Right. So polonium is a metal
What is?
or nonmetal? Polonium, lower right-hand corner.
It's a gray area.
Okay. Polonium is in the lower right-hand corner. Okay. It's not a perfect left-right half, right? Remember, most of your nonmetals are in the upper right-hand corner. So most metallic is the lower left-hand corner. So if you know those trends, you should be able to nail down the metallic character off of that. Okay. Lower left is most metallic, upper right is least metallic. Yeah?
Yeah.
Okay. Then what was the other one?
Atomic radius.
Radius. Okay. You aren't being asked to explain. I asked you to explain radius back in Unit 1. You don't need to explain it, you just need to know the answer, which is why just drawing in the arrows makes sense. Okay? As we go down a column, what's happening to our energy levels? They're increasing. Remember, there's nucleus first, second, third. So as we increase energy levels, what happens to the distance between the nucleus and that energy level? Further away, so the radius gets larger as we go down a column. Okay? Left to right, we get a flip on it. Okay? It gets smaller left to right. Okay? If you want to go back, does anybody want the explanation on that, or you just want the answer? Okay, you just want the answer. That's the answer. Okay? With that, we're officially done. If you still have questions, we got 15 minutes until someone else busts in. I'll continue to answer questions.
Number 54.
54. And Mary, for sure, we need to check your answers to make sure there isn't some mismatch, because I think I know what happened. And that's going to mess with a lot of your answer choices. 54, not a happy question, personally. I'm not happy with this question. I got this question wrong a couple times. So, the best way to answer this question that I found was actually writing out a chemical equation.
So that you get another number.
So, potassium metal, A solid, plus fluorine gas,
What is the log of 3 to get 36?
It's like pi. It's like pi. It's one of those numbers that
to
goes on forever
potassium
and ever and
fluoride.
ever and ever.
right?
Not really.
I don't really care what the phase is here.
It
Not a big
does
deal, so
have
let's just say
certain
solid.
numbers, but it's like, what is the log of 36?
What happened to the potassium as we went from reactant to product? It became potassium fluoride. What else happened to it?
It's still solid.
Okay, we said that phase wasn't important, so I'm going to erase that. This was everybody's least favorite chapter.
Potassium is 1 and the fluorine is 1. So they both are, one is negative 1 and the
Potassium is a +1 and the fluoride is a -1 in potassium fluoride. What is the case for that potassium?
they both
Upper right-hand corner in that purple box shows nothing. That potassium is
All by itself, it's nothing, because it's...
is a 0. There is nothing specified in that upper right-hand corner. Which means when we run this reaction, potassium is going from a 0 to a +1. What happened to it?
lost one of the, it becomes -1 and fluorine gains 1.
It lost 1 electron. What happened to the fluorine?
It gains 1 electron.
The fluorine gained 1 electron. Okay. Writing out the chemical equation gives you the answer. You don't write out the chemical equation, it becomes virtually impossible to answer this question.
So the answer I came up with D is
D, they're technically not sharing electrons. Okay. Sharing electrons means a covalent bond. That's an ionic bond.
Ionic doesn't share.
so potassium atoms and
Ionic is not sharing.
pretty much the same.
Potassium loses. Right. You have to
So
see
if we
what
go
balance
through,
equation.
the potassium ions lose electrons, the fluorine atoms gain electrons. The answer is A. B and C, those are just mind-boggling difficult, particularly in my opinion. This is, again, I see a lot of text. I tend to skip those questions because that text means I have to read and process those. What makes this even harder is that this is a true-false question. I have to read every single answer to decide true-false. That's a lot of work. Okay. So again, I personally know that I'm not very good with a lot of work. I'll move on. Okay. I'll go through and answer the questions where I can be like, I know that answer right away. And I'll come back to that. Okay. We're there less, actually I'm going to call it quits. I will head to